Welcome to Dark Sky Dive. Today, we embark on a journey to witness how humanity is building new eyes to see the invisible. When the Hubble Space Telescope first ascended to orbit, it fundamentally shifted the way humanity perceives the vastness of the cosmos. Then came the James Webb Space Telescope, unfolding its golden mirrors to reveal the ancient light of the very early universe. But for the relentless minds of modern scientists, looking back at the beginning of time is still not the final limit. Because every single answer that the universe reveals to us always drags along a multitude of even greater and deeper questions. To answer them, humanity is constructing the next generation of telescopes, machines so massive they challenge the very Earth itself. In the past, upgrading our view simply meant building bigger mirrors, better sensors, and writing slightly smarter software for computers. But this new generation is entirely different, designed to look deeper into time and analyze the faint atmospheres of distant worlds. They are built to analyze the atmospheres of strange planets and search for the elusive chemical signs of extraterrestrial life. This is no longer just pure astronomy. It is a desperate hunt for the answer to the question, are we alone? One of the most ambitious projects currently under construction is the Extremely Large Telescope, known simply to the world as ELT. With a primary mirror diameter of 39 meters, the ELT is so large it could easily contain an entire football stadium. It will gather tens of times more light than current telescopes, allowing us to see objects that were previously invisible. However, no single piece of glass can be that large. The ELT is composed of 798 segments. Each individual segment is polished to nanometer precision, creating a surface so smooth that it defies our understanding of perfection. The entire system operates like a living creature, continuously adjusting its shape thousands of times every single second to stay perfect. It constantly adapts to the wind, the changing temperatures, and even the subtle vibrations caused by the movement of the Earth. Earth's atmosphere is the greatest enemy of ground-based telescopes, blurring the starlight and hiding the sharp details of the universe. The new generation does not avoid the atmosphere. Instead, they defeat it using a revolutionary technology called adaptive optics. Lasers project an artificial star onto the sky, allowing computers to analyze atmospheric turbulence in real time with extreme accuracy. Then, the mirror physically deforms thousands of times per second to compensate for every single error caused by the air. The result is ground-based images that have a resolution equal to or sometimes even exceeding those taken from space telescopes. These new telescopes are not just about taking pretty pictures. They are designed to analyze the chemistry of distant worlds. They will search for oxygen, methane, water vapor, and the subtle chemical signatures that could indicate the presence of biological life. Some future telescopes will have the ability to block the blinding light of a parent star to see planets directly. This allows us to look directly at the tiny worlds orbiting stars, something Hubble could never do, and Webb is starting. Beyond James Webb, humanity is already planning space telescopes that are even more ambitious and larger than anything seen before. These machines will have mirrors larger than Webb, operating across multiple wavelengths simultaneously to capture a complete picture of the universe. Unlike Hubble, they are designed from the start to be serviced by robots or humans, ensuring a lifespan of decades. They allow for upgrades and replacements, meaning we no longer have to launch them and simply pray they never break. A new trend is emerging. Not just a single telescope, but a synchronized network of telescopes working together as one. Multiple telescopes placed on different continents or flying in formation in space can act as a single giant eye. This approach creates a virtual telescope the size of Earth, allowing for resolution that was previously considered physically impossible. It enables us to track extremely fast cosmic phenomena and observe events that last for only a few milliseconds. The data from these new telescopes is so massive that human beings can no longer process it manually or efficiently. Artificial intelligence is integrated to detect anomalies, filter out noise, and find things that human eyes would never notice. In the future, AI might be the first to detect signs of extraterrestrial life, not a human scientist. but an algorithm. However, these future generation telescopes also bring enormous risks, costing tens of billions of dollars and taking decades to build. They rely on technology that has never been tested before, making them the biggest gamble in the history of observational science. Just one small mistake, a flawed mirror segment or a stuck mechanism, could render the entire expensive project completely useless. Yet, humanity continues to build them because every civilization is defined by the brave questions they dare to ask. Future telescopes do not exist just to count stars or draw maps. They exist to answer where we came from. They help us understand how the universe began, if life is common, and where our future lies among the stars. One day, a future telescope will see something unexpected. A blue planet, a biological sign, or an inexplicable signal. And when that moment finally arrives, we will remember that it all started with silent blueprints and polished mirrors. It is the result of our undying desire to look further than our own limits and touch the edge of infinity. The extremely large telescope will be the world's biggest eye on the sky, a monument to human ingenuity and persistence. Its massive steel structure weighs thousands of tons, yet it moves with the grace and precision of a Swiss watch. Light travels millions of years to reach us, and this machine ensures that not a single photon is wasted or lost. While James Webb is a marvel of space engineering, the ELT on the ground offers a scale that space cannot yet match. For the astronomers who will use it, this telescope represents the culmination of their entire careers and their life's work. Located in the driest places on Earth, these telescopes sit above the clouds, waiting silently for the universe to speak. They can track fast-moving objects like asteroids near Earth, acting as sentinels that watch for potential threats from the dark. Understanding the orbits of these space rocks is crucial for planetary defense, and these new eyes are our best shield. Beyond defense, they peer into stellar nurseries, watching the violent and beautiful process of stars being born from dust. We will see solar systems in their infancy, witnessing the chaotic moments when planets are formed from debris and gas. This gives us a mirror to look at our own history, showing us how our Earth might have looked billions of years ago. Another giant, the giant Magellan telescope, uses 7 massive circular mirrors to achieve a resolving power 10 times that of Hubble. Its mirrors are cast in a rotating furnace, spinning molten glass to create a natural parabolic shape that is incredibly precise. The cooling process alone takes months, a test of patience required to create the most perfect optics ever made by humans. The 30-meter telescope joins this race, aiming to provide images 12 times sharper than the Hubble Space Telescope could achieve. Together, these 3 giants will cover both the northern and southern skies, leaving no corner of the universe unobserved. The collaboration between these observatories will create a golden era of astronomy, accelerating discoveries at a pace we cannot imagine. They will also probe the nature of dark matter and dark energy, the invisible forces that make up most of our universe. Understanding these forces could rewrite the laws of physics, explaining why the universe is expanding faster as it gets older. Physics is currently stuck at a crossroads, and these machines provide the experimental data needed to break through the deadlock. On the radio spectrum, the square-kilometer array will connect thousands of antennas to listen to the faintest whispers of space. It will detect radio waves emitted billions of years ago, mapping the hydrogen gas that fueled the very first stars. We are attempting to watch the cosmic dawn, the epoch when the universe transitioned from total darkness to blinding light. Closer to home, we are mapping the Milky Way in unprecedented detail, counting billions of stars to understand our galaxy's structure. This galactic census helps us understand the dynamics of spiral galaxies and the history of collisions that shaped our home. At the center lies a supermassive black hole, and these telescopes will study the extreme physics occurring at its event horizon. They will test Einstein's theory of general relativity in the most extreme laboratory available, the edge of a black hole. In space, concepts like LUVOIR aim to launch a mirror up to 15 meters wide, dwarfing everything currently in orbit. With the advent of heavy-lift rockets, launching these colossal structures is becoming a tangible reality rather than just a dream. We may soon see telescopes that assemble themselves in space, removing the size limitations imposed by the rocket's fairing. There are even plans to build observatories on the Moon, where the lack of atmosphere provides a permanently clear view. A liquid mirror telescope on the Moon could be immense, using spinning fluid to create a perfect parabola in low gravity. From there, we could look back at Earth or gaze uninterrupted into the deepest reaches of the cosmos forever. These projects take so long to build that the scientists who conceived them are often retired by the time they launch. It is a multi-generational effort, a cathedral of science built by one generation to be used by the next. The data collected is often made public, allowing citizen scientists and students around the world to make their own discoveries. We have entered an era where anyone with an internet connection can help hunt for exoplanets or classify distant galaxies. However, we face a new challenge. Satellite constellations are filling the sky, creating trails of light that interfere with observations. Astronomers are fighting to preserve the dark sky, developing software to clean images and negotiating with satellite companies. Preserving the darkness is essential, not just for science, but for our cultural heritage and connection to the universe. The ultimate goal remains the search for life. Finding a twin Earth is the holy grail of modern astronomy. We might find plants that are red or black, adapting to the light of a red dwarf star. Or perhaps we will find technosignatures, evidence of industrial pollution or artificial lights from an advanced alien civilization. The silence of the universe is deafening, but these telescopes are our best attempt to listen for a greeting. NASA is already planning the Habitable Worlds Observatory, a mission dedicated specifically to finding life on Earth-like planets. It requires stability so precise that it is equivalent to holding a laser steady on a coin across a continent. The cost of these missions is astronomical, requiring international cooperation and funding that spans multiple government administrations. Science has become a unifying force, bringing rival nations together to build machines that benefit all of humanity. From the perspective of the universe, there are no borders, only a single, fragile planet trying to understand its surroundings. As AI improves, it will begin to ask questions we haven't thought of, finding patterns in the chaos of data. We must be prepared for the unexpected, for discoveries that will shatter our current understanding of physics and reality. We are also building telescopes that look down, buried deep underground to catch ghost particles called neutrinos passing through Earth. Gravitational wave detectors listen to the collisions of black holes, feeling the tremors of space-time itself washing over our planet. By combining light, particles, and gravity, we are entering the era of multi-messenger astronomy, seeing the universe in full sensory. 50 years from now, we might have telescopes floating near Jupiter, or arrays spanning the diameter of the solar system. We could use the sun itself as a lens, bending light with its gravity to image the surface of exoplanets. This would allow us to see the continents and oceans of a world light years away, as if we were orbiting it. The scale of these ambitions reminds us that while we are physically small, our minds are capable of encompassing the universe. As dawn breaks over the mountains of Chile, the giant eyes close, having collected terabytes of secrets from the dark. But the work is just beginning, as supercomputers and scientists start to decode the messages hidden within the captured light. Every observation has the potential to rewrite textbooks and change our fundamental understanding of reality for future generations. Hubble showed us the galaxies. Webb showed us the beginning. The next generation will show us if we are alone. We are listening to the heartbeat of the cosmos, counting the pulses of dying stars and the breaths of newborn ones. It is a journey with no end, driven by the most powerful force in the universe, human curiosity. We build these cathedrals of glass and steel not to conquer the universe, but to humble ourselves before its grandeur. We are realizing that we are part of a vast, interconnected web, and our eyes are finally opening wide enough to see it. So look up at the stars tonight and imagine the giant machines that are watching them back right now. The future of astronomy is bright, and the discoveries waiting for us in the dark sky will change everything. From the deserts of Chile to the silence of deep space, our quest to understand the universe continues without pause. These are the mirrors that reflect our origins, and perhaps the mirrors that will one day show us our neighbors. As we stand on the threshold of this new era, we are ready to embrace whatever the universe decides to reveal. Thank you for joining us on this journey into the future of observation. The sky is not the limit. It is just the beginning. If you enjoyed exploring these giant eyes of the future, please like and subscribe to support our channel. This is Dark Sky Dive. Keep looking up, stay curious, and we will see you in the next deep dive.